How's it guys? So today we'll be covering model mechanics for neural networks. So no doubt you'll be very excited to start learning about neural networks. And indeed, the model class has gained some repute in recent years thanks to the extraordinary machine learning applications of this mathematical technology. And indeed, these achievements are for the most part truly amazing. However, as scientists, we need to treat this technology with a sober understanding of what it is and is not, what it is doing and not, and also when it is actually appropriate to use this technology. Right, so from the introductory perspective, which applies to this course, we'll focus on the application of neural networks so that you can get a feel for how these models actually work. Okay, so the premise here is that you learn and gain an understanding of what all the elements are that make the class, how learning is actually conducted for the model class, and then use standard software libraries to actually analyze real-world data. Okay, later on in honors and masters, we cover neural networks again, but from the mathematical perspective rather than the applications. And we both code up neural networks and relevant learning algorithms from scratch, and then it'll be your job to build and tailor code for very particular real-world or experimental applications. Okay. So you might want to stick around for that if you find all of this very interesting. So for today's lecture, we'll break up the model mechanics into three components. The first component will be model structure. The second component will be gradient descent and backprop, which pertains to the learning algorithm typically associated with the class. And then finally, we'll cover some details pertaining to network architecture. So let's jump in. Cool, so no doubt you would have seen a directed graph of a neural network before. Indeed, these directed graphs show up everywhere in the modern discourse around machine learning. Now, I have some mixed feelings about these, but it's probably best if we cover some ground before I actually present my cranky old man argument about these. So yeah, we'll just continue. Okay, so the starting point for explaining what the model structure of a neural network is in fact something that you should already be familiar with, a generalized linear model. Now recall that for generalized linear models, the predictors or features of a model are carried into the model in a simple linear parametric equation. Okay, so we take each predictor, we multiply it by a parameter, and we add them up, and then we add an intercept term. Okay, so using the design matrix language, this amounts to taking a row on the design matrix and post-multiplying it by a vector of parameters. Okay, so simple enough. Now, depending on the model, we might then have to apply an appropriate link function, which marries the linear component to the mean of the model, and or maps it to an appropriate range for the corresponding parameter of the underlying model distribution. Okay, so consider, for example, the special case of logistic regression. Okay, again, we have a linear component, which is carried into the model via a so-called link function. So that when we invert the link function, we have a sigmoidal function in the linear component that maps to the model distribution's parameter. So in this case, it'll typically be a success probability. So a number somewhere between 0 and 1. Right, and there you have it. This is your first example of a special case of a neural network. Okay, so to see this, let's draw a directed graph of the model. So first, we create some nodes representing the inputs, features, or predictors of our model. We'll then put one slightly off center and plug a 1 in where the predictor goes. Now, there's nothing special about this value. It's just there to carry the intercept term, as you'll see. We then create a single node adjacent to the input nodes and connect the input nodes to this node using directed edges, hence directed graph. We'll then label these edges with parameters of our model to indicate that the content of those nodes are then multiplied by the parameters and then passed to the new node. Okay, now because all of these edges point to the same node, we add them up. Okay, this represents the linear component. So we then allow the new node to apply some operation to its input, i.e. the linear component. Since our model is a logistic regression model, we apply, for example, a logistic function to the linear component, and that node then spits out a number between 0 and 1. This number is then the predicted response from our model, which we can then compare to an observed response. Okay. Now, looking at the resulting network, using the nomenclature from the world of machine learning, we could have just as well describe this as a neural network consisting only of a so-called input and output layer. Okay, that is, the first layer or column of nodes represents the inputs, and the node which processes the linear component and provides an output, which we can then compare to the observed response, that's called the output layer. Okay, so likewise, we could also rename the parameters to reflect the nomenclature from the world of machine learning, where the parameters associated with the predictors are referred to as the weights, and the intercept term is referred to as a bias. Now, though the names have changed, they operate in exactly the same way as before. They are just parameters of our model. So whenever you see weights and biases, all you need to think of are parameters. Okay, so this probably isn't quite as much network as you were expecting to see. So let's consider a slightly more general situation. Okay, so suppose now that we add two nodes adjacent to the input layer. We connect all of the inputs to each node using edges, all with their own parameters, or current nomenclature, weights and biases. Each of the new nodes now take a linear component and apply some operation to it. Okay, then we'll tag on a single output node that will take those two nodes as inputs, again using a linear combination to which an operation is applied in order to produce an output, which we can then compare to a response. Okay, so this is starting to look more like a neural network, right? But as you can see, the base elements are essentially the same as for a logistic regression model. Only this time we've added an additional layer of computation between the inputs and outputs. Now, this is the first so-called hidden layer of the network, which defines the model structure of our feed-forward network. Indeed, we are also free to add multiple layers if we wanted to. Incidentally, this is where the term deep learning originated, right? Referring to networks with many hidden layers. Now note that the dimensions on the number of nodes on the input and output layers are typically determined by the dimensions of the feature set and response variable. That is, if you had 3 features on a univariate response, you'll typically have 3 input nodes and then 1 node on the output layer which produces a prediction. As for the number of hidden layers and the number of nodes on those hidden layers, that is up to the statistician to decide, and hence why I say that this is the first aspect which relates to the defining of a model structure under a feed-forward neural network. Indeed, the way we'll communicate the model structure is by referring to the dimensions of the hidden layers. So for example, if our network had 2 nodes on a single hidden layer, it would be called a 2 network. If we had 2 hidden layers with 3 and 2 nodes respectively, we would refer to that as a 3-2 network. Cool. Okay, so in summary, we can construct a neural network using base elements such as linear components and simple operations applied in a structured way. Okay, now depending on the complexity of the problem that we're working on, you may need to define a massive network with multiple hidden layers with many nodes on each layer, or as is more often than not the case, a simple neural network with a single hidden layer and a handful of nodes will suffice. Okay, now, it is at this juncture that I will have my old man rant. Okay, so bear with me. Given the fact that the model class is referred to as artificial neural networks, and the network appears to depict something akin to graphical illustrations of biological neural networks, the temptation is to infer that artificial neural networks mimic the behavior of actual biological networks. Now, though I'm satisfied that the model structure was inspired by biological neural networks, and indeed it is a brilliant metaphor, I'm in no way convinced that they operate even in remotely the same way. Yes, the mathematical operation carried about by each node on the network could represent a very crude model for a biological neuron, but in reality, this is nowhere close to modeling the actual behavior of one, let alone a network of dynamically linked neurons. In fact, it is quite easy to see that this is the case, given that there are neither temporal nor stochastic elements anywhere in the network. Okay. Also, the fact that the directive graph of a model looks like a neural network, or a network of interlinked neurons, in no way precludes its function as a biological network. Okay. Indeed, before calling it a special case of a neural network, you probably had no reason to suspect that a logistic regression model, for example, would mimic a biological neuron, would you? Now, I don't dispute that graphical illustrations of model structures are useful. I will, in fact, at some stage ask you to create such an illustration, but what I would rather have you see when you look at a neural network is the recursive operation that defines it. Okay, so indeed, we could write the recursive operation that defines a neural network in a single line. So in vector form, this is as simple as the vector of nodes or activations in the Lth layer, where L is an index, is given by some operation or activation function, to use the machine learning nomenclature, applied to a vector for which each of the elements on that vector is a linear component in the previous layer's activations, i.e., or nodes, i.e. a set of linear components given by a weight matrix, which contains all the weights connecting the nodes on the L-1th layer to the Lth layer, post-multiplied by a vector of activations, or nodes, on the L-1th layer, plus a vector of bias terms. Okay, so you just get a vector of linear components to which you apply an operation or activation function. We then set the initial condition for this recursive function to be that the first layer of nodes corresponds to the inputs. We then iterate through however many layers we have defined for the structure and then terminate the recursive evaluation. Simple as that. So looking at it this way, there is nothing really special about this recursive operation. In fact, if we were to concatenate all the weight matrices and bias vectors into one long parameter vector, we may as well view it simply as a nonlinear function, albeit with lots of parameters. So, my rather dull but sober way to view the model class is simply as a very flexible class of nonlinear basis functions. Indeed, this view sits more squarely with the so-called no free lunch principle as it applies to machine learning. Okay, and that is that a priori, no one model class is always superior to another, or more useful than another. How appropriate and how well a model class performs is purely an empirical matter, which is determined by your data and nothing else. In this respect, neural networks are then no more attractive than, say, a Fourier basis, or even a linear basis to solve any one problem. In fact, in masters, we'll make some arguments as to why some linear bases might be preferable if you were to make any general claims about predictive performance. Okay, so that's my cranky old man rant over. I hope this doesn't take the magic out of it for you. This is still a very exciting mathematical technology, and hopefully by the end of this course, you will understand the technology well enough to dream up some awesome applications for your own research or workplace one day. Okay, cool. So we have a good understanding now of how to construct a neural network, but we still need a way to actually fit neural networks to data, right? Now, this amounts to finding the right set of weights and biases such that our network can learn to associate inputs with appropriate outputs. And again, noting that the weights and biases are just the parameters of our model, we thus just need a systematic way to find the correct configuration of parameters. Okay, so this is much the same as we do for generalized linear models, using, for example, the iterative weighted least squares algorithm. Now, as usual, this involves two components. So the first component is an objective function, which tells us how well a particular parameter configuration does at predicting the response. The second component is then an optimization procedure or learning algorithm, which finds the minimum of this objective function with respect to the parameters of our model. Okay, so that's the systematic way of finding the parameters. Now, in the case of neural networks, the appropriate learning algorithm for this purpose is the so-called gradient descent algorithm. Okay, now you guys should be familiar with Newton-Raphson. Okay, so as it is applied to minimizing an objective function, and indeed in the iterative weighted least squares algorithm that we covered earlier in 3043, you'll note that it is Newton-like in that it just replaces the matrix of second derivatives with an expectation. But regardless, both of these algorithms use the gradient of the objective surface and then some information about the shape of that surface in order to iteratively search for an extreme. Okay, in that case it'll be maximum likelihood. Now, gradient descent is also just an iterative optimization procedure, which, as the name suggests, uses only information about the gradient of the objective function. Okay, so the idea is that you start out with a guess for the parameter set, so i.e. a starting coordinate in the parameter space. You then apply a simple updating equation which looks at the gradient of the objective surface at that point and then uses information about that surface to step in the direction of the minimum. Okay, which is presumably downhill from there, hence gradient descent. Now, mathematically, the update is simply take the current position in the parameter space minus the gradient function of the objective, that is the gradient with respect to the respective parameters, scaled by some step size control parameter. Okay, and that's it. That's gradient descent. If you can evaluate the gradient of the objective function, you can iterate through this equation until you find a minimum. Okay, so that is, you keep iterating and you then apply some stopping criteria which relates to the minimum. So for example, one typically stops iterating when all of the gradients drop below some threshold level that you pre-specify. Alternatively, you can just monitor the value of the objective surface and then check whether it's converged to a minimum. Okay, cool. Now, an important component here that you should familiarize yourself with is the step size control parameter. Indeed, this is another term which has a different name in the world of machine learning, where people in the field of numerical analysis, for example, would use step size control like I have here. Machine learners use learning rate because, well, metaphor. In any case, what you really need to know about this is as follows. A large learning rate means fast learning, but the algorithm might become unstable and or oscillate around the minimum. A small learning rate means slower learning, but you're more likely to find the minimum and less likely to jump around in the parameter space in every which way which is not the minimum. Okay, so a balance needs to be struck between having the algorithm converge quickly or learn quickly and having it actually find a minimum, i.e. actually learn something, and that can take very long. Okay, so what's the story with backpropagation? No doubt you will have heard this term floating around. Okay, well, backpropagation is a procedure which allows us to evaluate the gradients of an objective function when the predictions are supplied specifically by a neural network. Okay, so suppose, for example, we attempt to solve a regression problem using a neural network. We can construct an error measure by, for example, summing up the squared distances between the predictions, which are provided by the final layer of our network, and the observed responses. Now, in order to fit the neural network, we can then find an optimal configuration of the parameters simply by minimizing this error measure or objective function. Now, if we wanted to use gradient descent to do this, we'll need to evaluate the gradients of this function with respect to each of the parameters in the network. Now, backpropagation refers to the recursive procedure by which gradients are calculated through the layers of the network using the chain rule. So this is how it goes. First, we evaluate the quote-unquote errors with respect to the parameters in the final layer of the network. We then, using the chain rule, can propagate these errors backwards and evaluate gradients with respect to parameters in layers earlier in the network. Okay. Now, this seems very complicated at first, but the procedure is quite elegant in that after some mathematical manipulation, you arrive at a simple recursive procedure, not too dissimilar from evaluating the neural network forward in the first place. Indeed, we can write the recursive equations for calculating the gradients with respect to each layer's weight matrix and bias vector in vector form in as little as a couple of lines. Now, you don't need to worry about this. You don't actually need to know these equations. We'll derive them and use them in honors. But now you'll know what virtually all software packages do in the backend in order to fit neural networks. And indeed, you'll invariably see the words backpropagation with gradient descent in some way or form of another in the literature and software manuals that you'll be using. Okay, so in closing, it is worth noting that though it would seem that backpropagation is really nothing more than a clever application of the chain rule, the implications of this algorithm are substantial in that it allows us to very efficiently calculate the gradients of large networks. And indeed, this is what makes many of the exciting modern day applications of neural networks computationally feasible in the first place. So, very cool stuff. Cool, so we now know how neural networks are constructed, and we also have a learning algorithm to train our neural networks. But to complete the story, we need to look at some finer details, which together with the neural network dimensions, so i.e. 5.2 or 7.5.3 network, constitute the network architecture. So first up, the so-called activation functions, which are applied to the various layers of the network. Now recall that at the start of this video, where we discussed the structure of an artificial neural network, we noted that the linear elements have some operation applied to them in each of the nodes of the network. Now, in the world of machine learning and neural networks, these operations are referred to as activation functions, where the nomenclature again borrows from the biological neuron network metaphor, in that the activation function is said to take the signal from the linear component and in likeness to a biological neuron process that signal and then activate to produce an output signal. Now, in reality, this is just a simple mathematical operation that typically maps the input to a finite range. And again, the distinction between the metaphor and reality is quite easy to see in that the activation in a biological neuron actually occurs when a threshold potential is exceeded. And again, this is an event which is in actual fact stochastic in nature, as opposed to an instantaneously true mathematical expression as it is here. But in any case, we'll entertain the nomenclature. Right, so although there are many types of activation functions, each with their own benefits and drawbacks, they are typically all of sigmoidal form. So that is, they take values on the real line and then map them according to a sigmoidal shaped function to a finite range. Now, the most common specification, which you are already familiar with, is the so-called logistic activation function, which just maps from the real line to the interval 0 to 1. Another very popular activation function is that of the hyperbolic tangent function, or tanh for short activation, which maps from -1 to 1, with the advantage of using such an activation function being that it permits negative values and more easily evaluates to 0 than, say, a logistic activation function. So that is, although logistic activations can produce values too close to 0, this will only occur when the gradient of that activation function is small, which is disadvantageous for training. Okay, so you can see the advantage of using something like a tanh function. Then, finally, another common specification is that of the so-called rectified linear unit, which is essentially the positive part of a linear function and 0 elsewhere. Okay, now, though the specification might seem strange, it does have some merit for training, since wherever the function is non-zero, its gradients are both easy to evaluate and do not suffer from the shrinkage that, say, logistic or tanh functions do in their extremes. Okay, they also may have some advantages for learning theory, or from the learning theory perspective, due to how networks with such activations actually partition the feature space. One drawback, though, is that ReLU activations are discontinuous and, strictly speaking, not differentiable everywhere. Okay, so as such, when we implement numerical procedures such as gradient descent or something else during learning, we typically just squint while closing one eye as we use an expression which is not quite its derivative, and then use our deep understanding of numerical analysis to sweep any instabilities under the rug. Or alternatively, we might just employ an algorithm which is better suited to deal with such discontinuous elements. And indeed, this issue shows up again anyway for a particular kind of regularization, as we'll see later. Now, typically, in the case of standard feed-forward neural networks, A statistician or machine learner will specify one type of activation function for all of the hidden layers. But as you will find in more advanced applications, such as, say, convolutional neural networks, one will typically apply various types of activation functions or operations in sequence in order to achieve a particular effect and improve learning in your model. But we cover more on this in honors and masters. Cool. Then finally, we need to consider the output activations and the objective functions which apply to the output layer. Indeed, the type of response variable we have for any particular modeling problem will dictate which activations we can, or rather should, again more on this in honors, apply to the output layer, and also what constitutes an appropriate objective function. Cool. So in the case of a regression problem, so i.e. Responses on a continuous scale, we simply apply a linear activation to the output layer. So that is, the activation does nothing and simply returns its input. Okay. Now this is not to be confused with the rectified linear units that we discussed earlier. This is just a standard fx equals x function, which of course maps from the real line to the real line and hence produces a prediction at the output layer, which is on the same scale as a real valued response. Okay. Now note that the linear activation is not to be used anywhere else. Okay. If you use linear activations everywhere, for example, you simply end up with an overdetermined system or overdetermined linear system, which won't be particularly useful. As for an objective function, in the case of regression problems, we can just use the standard mean squared error objective function to measure how far our predictions are from the observed responses, and we can then use gradient descent to pursue a minimum for that objective function somewhere in the parameter space. Okay, right. Then, in the case of categorical responses, we make use of either the logistic function or activation function, and that will be when the response category can take only one of two values. Or alternatively, we can also use the so-called softmax activation, when the response can take on multiple categories. Okay, so this follows since in order for our network to produce predictions for the categorical response, the outputs on that layer must behave like a distribution, with the probability attached to each outcome being subject to the constraint that all the probabilities on the output layer must sum to 1. Now, if you look at the structure of, say, the softmax activation, it should be obvious why that constraint would be satisfied by that particular activation function. Now, in the case of categorical responses, we also need to tailor the objective function in order to cater for the fact that we are comparing a discrete distribution to a categorical outcome. So for these purposes, we use the so-called cross-entropy objective function. Now, as mentioned in the tree-based methods section before, this is not to be confused with the Shannon entropy. In the case of cross-entropy, the measure is based on the observations and the predictions which are compared directly. And even though these expressions look quite similar, they do not operate in quite the same way. So important difference there. In this case, we'll use cross-entropy. So to summarize model mechanics for neural networks can be seen as a useful nonlinear basis characterized by the dimensions and number of hidden layers and activation functions or operations applied in each layer. Then, depending on the type of learning problem you are tasked with, one then chooses an appropriate activation for the output layer and an objective function specification, which you can then pass to an appropriate learning algorithm. Okay, now these learning algorithms typically involve some form of gradient descent, which in turn applies backpropagation in order to evaluate the gradients of the objective function with respect to the weights and the biases of the model. And that's really all there is to it. So I hope you found that interesting. In the lab session that follows, we'll play around with some model structures for neural networks and do some basic analysis. Then in the next lecture, we'll cover managing complexity for neural networks. Cheers.